Hello all, welcome to the new lecture of section 3.8 Hilbert-Smith theory. In this section we mainly discuss about the properties, one of the nice properties of characteristic functions, that is the orthogonality of distinct characteristic functions over open interval AB. Up to the last lectures, we have discussed about the second kind Fredholm integral equation with the separable kernels and the nature of solution of Fredholm integral equations having separable kernel. But in many of the cases, the kernel k of x theta of a homogeneous Fredholm integral equation is not separable. In particular, if k of x theta has a different analytic expressions in the intervals for which x is less than theta and x greater than theta. There are generally infinitely many characteristic numbers lambda n for n equal to 1, 2, 3, etc., each corresponding to a characteristic function defined with an arbitrary multiplicative constant. In certain cases, a given characteristic number lambda k may correspond to two or more independent characteristic functions. So in this lecture, we mainly discuss about certain properties of these characteristic functions. Characteristic functions are actually the solution of the non-trivial solution of the homogeneous Fredholm integral equations corresponding to the characteristic number lambda. The first of the properties is lambda equal to 0 cannot be a characteristic number of the homogeneous Fredholm integral equation y of x is equal to lambda integral a to b k of x theta y of theta d theta. Since if lambda equal to 0, we have the Fredholm integral equation has only the trivial solution y of x equal to 0. So that cannot be the trivial solution, which is not a characteristic function. Therefore, lambda equal to 0 cannot be a characteristic number. Now the second property, that is the Hilbert-Smith theorem, which the statement is the characteristic functions corresponding to distinct characteristic numbers are orthogonal over the open interval AB. Characteristic functions corresponding to distinct characteristic numbers are orthogonal over the open interval AB. This is a very important result, which is known as Hilbert-Smith theorem. Now we try to prove this result. Let ym of x and yn of x are characteristic functions corresponding to different characteristic numbers lambda m and lambda n of the Fredholm homogeneous Fredholm equations. That is, ym of x and yn of x are characteristic functions respectively of corresponding to the characteristic values lambda m and lambda n of the homogeneous Fredholm integral equation equation number 1, that is y of x equal to lambda integral a to b k of x theta y theta d theta. And one more thing, it's very important to suppose that the kernel is symmetric. Kernel is symmetric, so that k of x theta is equal to k theta x. Since ymx and yn of x are characteristic functions corresponding to lambda m and lambda n, we can see that these must satisfy the equation number 1, that is ym of x is equal to some lambda m into integral a to b k of x theta ym theta d theta, and yn of x is equal to lambda n integral a to b k of x theta yn theta d theta. Now multiply equation 2a by yn of x and integrate the result from a to b with respect to x. We have integral a to b ym of x into yn of x dx is equal to lambda m integral a to b yn of x into in bracket integral a to b k of x theta y m of theta d theta into dx. Substitute this as equation number 3 or put it as equation number 3. Now if the order of the integration is reversed, in the right hand member of equation 3 becomes lambda m into integral a to b ym of theta, then in bracket integral a to b k of x theta yn of x dx bracket close into d theta. So that means we have reversed the order of integration. First we calculate integral a to b k of x theta yn of x dx, then integral a to b, multiply that with ym of theta, then integrate. And we know that the kernel is symmetric, so we can have the inner integral as k of theta x integral a to b k of x theta yn of x dx becomes integral a to b k theta x yn of x dx. So the equation 4 will be in that form and name it as equation number 5. Now comparing the inner integral with the equation 2b. In 2b we have yn of x is equal to integral a to b lambda n integral a to b k of x theta yn of theta d theta. And if we write this as yn of theta, then we have lambda n integral a to b k of theta x yn of x dx. So comparing this, we have k of theta x yn of x dx can be written as 1 by lambda n into yn of theta. Integral a to b k of theta x yn of x dx can be written as 1 by lambda n into yn of theta. So we have from equation number 5 integral a to b ym of x into yn of x dx equals lambda m by lambda n into integral a to b ym of theta into yn of theta d theta. Since the integrals, both integrals in this equation are equivalent because x and zeta are dummy variables here, we can have this as lambda m by lambda n minus 1 into integral a to b ym of zeta into yn of zeta d zeta. Since lambda m and lambda n are distinct characteristic numbers which cannot be 0, we have this becomes 0 only if integral a to b ym of x into yn of x dx equals 0. Since lambda m and lambda n are distinct characteristic numbers. So we have the characteristic functions corresponding to distinct characteristic values are orthogonal over the open interval AB. And one more thing, it's very important to keep in mind is that the kernel must be symmetric, then only we can have this result. So equations with a asymmetric kernel, there is no result. This is applicable only to symmetric kernels. So this is a very simple proof. Now we move to the third property, that is the characteristic numbers of Fredholm equation with a real symmetric kernel are all real. That means the real and symmetric kernel, Fredholm integral equation with a real and symmetric kernel have all the characteristic numbers real. There is no imaginary characteristic numbers or complex imaginary characteristic numbers for Fredholm equation with a real symmetric kernel. Proof is by contradiction. We assume that if possible, there are some imaginary characteristic numbers, say lambda m. Let lambda m were an imaginary characteristic number corresponding to a complex characteristic function, some ym of x. So the relation connecting the distinct characteristic numbers and a corresponding characteristic function is actually this one, equation number 6, lambda m minus lambda n into integral a to b ym of x yn of x dx equal to 0. So keep that result in mind. Now we need to prove that Fredholm equation with a real symmetric kernel have all the characteristic numbers real. So if possible, we assume that lambda m is an imaginary characteristic number corresponding to a complex characteristic function ym of x. Then the complex conjugate number lambda m bar would necessarily also be a characteristic number corresponding to the characteristic function ym of x, which is the complex conjugate of ymx. So if there is imaginary characteristic number, then its conjugate will also be a characteristic number corresponding to the complex conjugate function, characteristic function ym bar of x, which is a complex conjugate of ym of x. Now consider the relation 6, which relates the characteristic numbers and characteristic functions lambda m minus lambda n into integral a to b ym of x into yn of x dx equal to 0. In this replace lambda n by lambda m bar, the complex conjugate, and yn of x by ym bar of x. Then we have equation number 2, lambda m minus lambda m bar integral a to b ym of x ym bar of x dx equal to 0. Being an imaginary number, we can write lambda m as being a complex number, we can write it as lambda m equal to alpha m plus I beta m, and therefore ym of x is and is fmx plus I gm of x. Then lambda m minus lambda m bar will be 2I beta m. Then ym of x is this one, then ym bar of x will be fm of x minus igm of x, and ym into ym bar will be a square plus b square form. So this will be fm square plus gm square, which is always greater than or equal to 0. Now equation number 2 becomes 2I beta m integral a to b fm square plus gm square dx equal to 0. Now ym of x is a characteristic function. It cannot be trivial. So ym of x not identically equal to 0. We have fm not identically 0 and gm not identically 0. So fm square plus gm square is always positive, and therefore integral a to b fm square plus gm square is also positive. So equation number 6, this becomes 0 implies not 6, equation number 3. So equation number 3 implies beta m is equal to 0. So beta m means we have written lambda m as alpha m plus I beta m. So beta m becomes 0 means lambda m equal to alpha m, where alpha m is a real value. So the imaginary part of lambda m must vanish. That means all the characteristic numbers are real. Characteristic values or characteristic numbers of a Fredholm equation with a real and symmetric kernel are all real. One more thing, notice that the Fredholm equation with a non-symmetric kernel may possess non-real characteristic numbers. So equations with a non-symmetric kernel may have non-real symmetric kernels, symmetric numbers. Non-real characteristic numbers. So we have discussed about mainly about the properties of characteristic or nature of characteristic functions and related characteristic numbers. So let's stop here. Thank you. Thank you all.